Last class, we have discussed about principles of electromagnetic energy conversion. This class, we discuss about some of the basics of DC machines, such as magnetic field, laws applicable to motor and generator, and Faraday's law of electromagnetic induction. You are expected to refer Electrical and Electronic Technology by Edward Hughes, pages between 132 and 146. Magnet was produced from the ore magnesian stone, hence it is named as magnet. Magnetic field is the region around the magnet where the moving charge experiences a force, whereas the magnetic flux shows the strength of magnetic lines produced by the magnet. Refer figure 1. The bar magnet and its associated flux lines shown. The flux lines emerge from the North Pole and enter into the South Pole. Magnetic flux lines, also called as magnetic field lines. Some of the properties of magnetic flux lines are: flux lines always form a closed path, and these lines never intersect each other. Lines of flux which are in parallel and in the same direction repel each other. Oersted in 1820 discovered a phenomenon: whenever a conductor carries an electric current, a magnetic field is produced around that conductor. Departing current is the one which is flowing away from us, and approaching current is the one which is coming towards us. Departing current inside a conductor is indicated as cross, and approaching current is indicated as dot inside a conductor. Consider a horizontal plane. Departing current will be entering into the plane, and approaching current is coming out of the plane. Refer figure 3 indicates magnetic field due to a departing current in a straight conductor. Departing current is indicated as a cross inside a conductor. In case of a departing current, the flux lines are clockwise direction, indicated in clockwise direction. In case of approaching current, the flux lines will be of anti-clockwise direction. Both in case of departing current and in case of approaching current, the field lines are represented as concentric circles. Direction of current and direction of magnetic field can be found in two ways. One is using Maxwell's corkscrew rule, another one is using right hand grip rule. Figure 4 indicates the Maxwell's corkscrew rule. Look at this. Corkscrew rule is placed alongside of the conductor carrying the current I. In order to move the screw in the same direction as that of the current, it has to be rotated clockwise. It has to be turned clockwise. This indicates the direction of the magnetic field from the same side. That is, I am referring the left hand side. The direction of the current is from left to right, indicated by this arrow. Alternatively, we can find the direction of the current and magnetic field using right hand grip rule. Referring figure 5, we are gripping the conductor on the right hand and thumb outstretched and outstretched and parallel to the conductor and indicates the direction of the current, and curling fingers indicates the direction of magnetic field. Whenever a conductor is placed in a magnetic field, force will be developed. Look at figure 6 and 7. Figure 6 says the conductor is placed in a magnetic field and the conductor does not carry any current. So that is what, there is no force developed in this diagram. In case of figure 7, look at the conductor carries the departing current, and we know this carries the clockwise direction of flux, and at this side the flux is added together. And look at the top side of the conductor, the flux lines are being strengthened, and at the bottom the flux lines are opposite. Here the flux lines goes from north to south pole, and here clockwise direction, so both are opposite and cancel each other. That is what demagnetizing effect. Here it is magnetizing effect being shown in the diagram. If either the current or the direction of the field is reversed, then the direction of the force is also reversed. If both the current and field are reversed, the direction of the force remains unchanged. Fleming's left-hand rule, also called as a motor rule, which gives the direction of force experienced by a conductor. Refer the figure. We keep the fingers of left hand, namely the thumb and the forefinger or the pointing finger and the middle finger. All these three fingers are mutually perpendicular to each other, meaning thumb and forefinger, look at the angle is 90 degree. That is orthogonal. Similarly, forefinger and middle finger 90 degree, and similarly thumb and middle finger 90 degree. That is what the reason we say mutually perpendicular to each other. If we keep so, thumb indicates the movement of a conductor and forefinger indicates the magnetic flux lines from north to south pole, and the second finger indicates the current. Force on a current carrying conductor at right angles to a magnetic field is increased whenever the current in the conductor is increased, and when the magnetic field is made stronger by bringing the magnet nearer to the conductor. We can write is equal to BIL newtons. B is the magnetic flux density in Tesla or Weber per meter square. 1 Tesla is equal to 1 Weber per meter square. I is the current in ampere and L is the active length of the current in meter. Active length meaning, let's see, we have far magnet north pole and we have a south pole. This indicates the flux lines, and if the conductor is placed inside a field, and this portion of the conductor, I am referring this portion of the conductor, is only placed inside a magnetic field. So this refers the active length of the conductor. That is only being considered. Referring the flux density equation, which is the ratio between the flux by area. Figure 9 indicates whenever area increases, the flux density will get decreased, and whenever an area decreases, more flux density in a small area. Look at A and A prime indicates larger flux densities, the area becomes smaller, and look at the portion B and B dash, where area is larger and the flux density becomes smaller. In 1831, Faraday showed that an electric current could be produced by the movement of magnetic flux relative to a coil. He also showed that the magnitude of the induced EMF is proportional to the rate at which the flux passed through the coil is varied. So he found two laws. The first law states that whenever a conductor cuts lines of magnetic flux, whenever a conductor cuts lines of an EMF is the conductor. And in the second law, the magnitude of the induced EMF is proportional to the rate of change of flux linkages, which is given by E is equal to minus N d phi by dt. If only one conductor, we can say N equal to 1. If number of conductors are connected in series, we can consider capital N. And minus sign in this equation indicates the Lenz's law. The induced EMF always opposes the cause. That is what we use in this equation. E is the EMF in volt, and N is the number of and d phi by dt, the rate of change of flux in Weber per second. Two methods are available for reducing the direction of current of the induced or generated EMF. One is we discussed in the previous slide, Lenz's law, and another one is the Fleming's right hand rule, also called as a generator rule. If we keep the three fingers, namely thumb, forefinger, and middle finger of our right hand, thumb indicates the motion of the conductor, and middle finger indicates the field lines flowing from north to south pole, and middle finger indicates the induced EMF. So far, we have discussed about some of the basics of the DC machine, namely magnetic field and its some of the characteristics, motor rule, generator rule, and the Faraday's law of electromagnetic induction. In the next class, we will be discussing about the analogy between electric and magnetic circuits. Thank you.